Hello, we can start this second session of the Inizio webinar, and the next speaker is Lukaš Ustrnul, the Tallinn University of Technology. I hope I have read correctly the name. And the title of the talk is Supramolecular Studies of Host Molecules. Lukaš, the desk is yours.
Hello, everyone. We'll try to share the...
Okay, great.
So you can hear me nicely?
Yeah, well, the volume is quite low. So if you can increase the volume of this, of the microphone is better.
I'm not sure how to do that. Microphone. So is it okay or?
Yeah, now it's okay.
Okay, I will just try to speak loud enough. So hello everyone. I hope you had an enjoyable break. Now I will talk about supramolecular complexes of our chiral hemicucurbitures. So in general, what I'm doing in Dana Af's group, so colleague of Dima, so I will be showing some structures which you've seen maybe in the presentation. I'm mainly focused on those supramolecular interactions and studying them and so on. And I believe that nowadays already everybody knows that supramolecular chemistry is dealing with non-covalent interactions. So I'm not going to do the introduction for that, but I would like to make a little bit wider introduction for the area in general. I have a feeling there is sometimes confusion in the names which we are using. We are just calling it cucurbiturials, although we biotin-ureal, for example, and so on. So let me just make it straight. What are differences and why those are important? Because from the point of supramolecular chemistry, those molecules can be really different, although on the first sight and from the point of synthesis, they are kind of similar. So first cucurbiturials, because those were the first ones which came. First cucurbiturial was actually prepared already in the beginning of the previous century by Berendt, but it's very insoluble compound, so elementary analysis, and that was all. So they didn't know the structure. And later in 80s, this synthesis was reproduced, and Mock and his colleagues got even the crystal structure. So as you can see here, I will point there. So yes, so as you see, this is glycoluryl unit, and it's a very simple molecule which is connecting to urea moieties. And then if you do the reaction in the acidic conditions with formaldehyde, you will get the macrocycle, different sizes. And there is 2 rows of those methylene bridges. So the molecule looks roughly like this, depending on the size, the cavity bigger and bigger, but the height of the molecule is the same because still having just this one part monomer unit. And where comes from this weird name, cucurbiturial? Well, when they solved the crystal structure, it resembled them a pumpkin. And cucurbite means pumpkin in Latin. So basically, we are talking about cucurbiturials, we are talking about pumpkins. So maybe I will be in some moments talking about pumpkins because it's hard to all the time saying cucurbiturial because it's like tongue twister. And often we shorten it also just as a CB. So let me show you a few examples of the use of those molecules. So they were prepared properly in 80s, and already shortly after that it was shown that the used, for example, for catalysis. So this is a type of reaction, like a click reaction, which is nowadays very popular. So you can see that it was used for this already in the 80s. Nowadays, the scope of the use of cucurbitacills is very wide. It exploded after year 2000, I would say. And you can find plenty of articles where the interest is not anymore in the cucurbitacil itself, but it's somewhat utilized in different systems. So, for example, this is a way where you can have derivatized polymer strains, and you make cross-linking by a supramolecular interaction with 8-membered macrocycle, because this one can fit 2 different guests at the same time. And then last example of some sort of probe, you can have a complex of a cucurbitacil with some dye, and in the solution, the preference of binding goes for those butanes and isobutanes in the water. So if you will bubble the gas to the water solution, the butane pushes this dye out of the cavity, and it's quenching the signal. And this can be repeatable, so you can use the cucurbitacil in combination with the dye as a sort of sensor for the presence of those small alkanes in the solution. Now let's go further. So later on, somebody was thinking, okay, there is 2 rows of methylene bridges, but actually to make a macrocycle, you don't just 1. So let's cut this molecule sort of in half. That's what was done by Bushman. And you can see here this most simple hemi-cucurbitacil molecule. So it's hemi because it's half of cucurbitacil, and often we call it just hemi-CB, or you can see also this are using for our cyclohexanol hemi-cucurbitacils, because they have this cyclohexanol group here. And those were prepared in our group, and it's actually the first hemi-cucurbitacil which was prepared, and it's inherently chiral. We can prepare both of the enantiomers just by using proper monomer. And then a bit later, Pitelkov came with this biotinuryl. I have seen both of those molecules already in Dima's presentation. Biotinuryl is really nice from the point from the natural compound biotin L-uryl. And now I want to stress out the differences between cucurbitacils and hemicucurbitacils to make it clear for you why it's good to not to mess them up between each other, because they are really different, although the structure can be on the first sight pretty similar. So as I already said, for CB, there is 2 rows of those methylene bridges, and that makes molecule really rigid. On the other hand, when we have just 1 row of methylene bridges in the hemi-CBs, there is much more flexibility. The second big difference is in the way how the binding, especially inside the cavity, works. So for normal cucurbitacils, they prefer to bind inside the cavity neutral guests. So here you can see that inside the cavity, there's basically an alkyl chain, and then tops some other moiety, and it makes pseudorotaxane. But for the hemi-CBs, it's typical that they bind anions in their cavity. You will not see binding of anion to normal CB. You will see it just for hemicucurbitacils. And that's because in the case of hemi-CBs, it's sort of like inverted cucurbitacil when you think about it, and when you properly how those glycoluryl units are twisted. So for CB, the hydrogen atoms are pointing out of the cavity, but in the case of hemi-CBs, at least some of the protons are directing inside the cavity. So actually, the stabilization of this anion is thanks to those CH anion bonds. The next difference is that for the cucurbitacils, there is this nice carbonyl portals from both sides, and they bind very strongly cations. In the case of the hemi-CBs, there is no clear portal. There is different derivatives of hemi-CBs, so there is actually nothing specific like in the case of normal cucurbit. And then last difference, which I want to stress out, is this equatorial outside area, where for cucurbiturills there is those hydrogens, and it can make very weak but still visible bonding between some partly negatively charged compounds, and it's pretty usual if you see the cucurbituryl crystal structure that they are in this sort of shape that one carbonyl portal is sticked to the wall of the molecule of the cycle. In the case of our hemi-CBs, which we are working with all the time, there's equatorial area, also this urea moieties, but actually before we started to dig into this, there was no previous studies showing interactions from outside of the molecule, those urea moieties, or more specifically carbonyl oxygens of the moiety. And there's one more difference which I want to stress out now, just between two different hemi-CBs. One is this cyclohexano, which was prepared in our group, and the second one is this biotin prepared by Pitelkov. But as you saw in Dima's presentation, we are working with this one quite a lot at the moment too. So for cyclohexano hemi-CB, we have two different sizes which we can easily prepare, and basically for us it doesn't matter if we are making RR enantiomer or SS, because both of the starting materials are kind of same, difficult to prepare. In the case of biotin, of course you could make this non-natural enantiomer of biotin, but it would be more difficult, and it's not so readily available on the market as normal biotin. So this is one like flaw in it. The other thing is that it has just one size, just a 6-membered macrocycle. So of course the size of a cavity is influencing how big anions are preferred for binding to the cavity. And on the other hand, the benefit of a biotin is that there is much more groups which you can functionalize. For the cyclohexano hemicucurbituryl, it's really hard to make some substitution, and it wasn't shown yet that point of view cycle and then somewhat derivatize it. And now I want to say something about our publication from previous year, which was about porphyrins ternary complexes. I don't want to tell introduction for porphyrins, because we have seen already two really nice presentations about porphyrins, but I think this paper is quite nice. We focused really just on ternary systems where all three components are something different, and we shown the examples of different cages and capsules, and also some molecular machines like this oscillator, some other type of oscillators and rotors which can, for example, work as a catalysts. There's plenty of sandwich kind of molecules in the literature which you can find. Also, what is pretty interesting, a lot of we know that porphyrins are in a hem, so some of the porphyrins can carry the oxygen, but to have something what will really work as artificial blood, you have to actually secure this space around porphyrin from some oxidations and so on. So there was efforts, and there was utilized some cyclodextrin derivatives for making this sort of artificial blood, and also very field are the chiral memories, whereby combining two different porphyrins and applying chiral template, you can keep this chiral information in the solution even after the template removal. So if you are interested in porphyrins and supramolecular chemistry, I will be happy if you will take a look on our article, because there is plenty of interesting stuff, I guess. And now let me present something from our research. I will focus on 2 articles. One was made mainly by Nele Konrad, who is our PhD student, but also there was plenty of other people working on it. And the main supervisor of the work was Dima Kananovic, who talked before the break. And the second publication will be me. So in Nele's case, she was studying those Takemoto catalyst derivatives and their interaction with the porphyrin, zinc porphyrin more specifically. In my case, I had the same porphyrins, but I was studying the interaction to our cyclohexano MECB. In both cases, we saw that there is an induction of CD spectra, which means that the porphyrin is becoming chiral, but I will get to that later. So first of all, the Nele's publication. In this publication, as I already said, we had this Takemoto catalyst and the porphyrin, and she studied their interaction. The tricky thing here on our guest is that there is several groups, several places where the interaction with the porphyrin could occur. So there was done control experiment with this simple thiourea moiety, and it showed us that the binding is very weak, just 17. And then when we did this titration, this was made by NMR titration, by the way, and then for the porphyrin with the Takemoto, studied mainly by UV vis titrations, and from fitting 1-to-1 binding, Nele got 2,300, which is far higher value than 17, right? So it means that this urea moiety doesn't give almost any interaction compared to this amino group here. So this has to be definitely the preferred binding site. However, it's clear that this Takemoto can give some additional interaction. At least some pi-pi stacking should be very easily possible between this phenyl group and phenyl groups of a zinc porphyrin, or if it's with this with its pi system. So knowing from literature that in the cases you have a chiral compound interacting porphyrin through a multiple point interaction, not just through the coordination to metal, but with some additional place to interact too, there often appears some induction of chirality. So Nele checked CD spectra. Of course, for pure zinc porphyrin, there is only noise without any CD, but binding to the Takemoto derivatives, there is rather weaker, but very nice and clearly visible induction of CD signal, which means that this non-chiral molecule became chiral, and that's what was already talking about Chris, that you can actually induce the chirality, and maybe some porphyrins are better for that than the others. So in this case, we had the most usual zinc porphyrin, zinc tetraphenylporphyrin, I'm sorry. And after we got this result, we started to think where it is appearing, where is actually this other interaction and so on. First of all, we thought what can be the conformations of this Takemoto. So here is the 3 conformers, which should be the most abundant. And we asked our colleagues who do in the computational chemistry to try to find out the most abundant conformers and calculate their. And this is what we got. I'm not showing structures on of those conformers because there was mainly very small differences, but it was based on what you saw on the previous slide, that they were either syn or anti or anti and so on. So the first conformer was actually like 50%, and it showed this designate signal in CD. This is from calculation, of course. And all the others, you can see that more or less they are showing just negative CD. If you combine those spectra, taking in account the abundance of particle conformers, you get this calculated spectra, which is really nicely corresponding to our experimental result. So I think the most interesting result from Nell's paper is that we can actually got by computational chemistry pretty nice results and predictions of a CD spectra. And now let me move to a second study where I was using this cyclohexanohemicocubitorial. Here is all the structures which was used. Well, okay, for our cyclohexanohemi-CB, we were using also SS enantiomers to see that, that the induction of chirality is really caused by the macrocycle and not by something else. So this is how the complex looks like. Main interaction is between the carbonyl oxygen, urea moieties, and the zinc. And here is a crystal structure. So in general, we are usually getting structures which are either 1D polymers, or we can get also something like this, where we have a 2-to-1 ratio. So those two porphyrins are bound to this macrocycle, but you can nicely see from these crystal structures that one macrocycle can be surrounded up to 4 porphyrins. This is for the case of the 8-membered macrocycle. In the case of 6-membered macrocycle, we did not get this type of crystal structure, but when we tried to fit the molecules, it seemed like that there should fit 3 molecules of porphyrin. So of course, the solid and the solution can be something completely different, but this gave us a hint that there could be up to 4-to-1 ratio, the binding in solution. And also, when we studied the binding in solution, we saw a nice shifting of all the signals from our macrocycle. So this part is basically the cyclohexano groups, and those two spikes here are for those methylene bridges between urea moieties. So you can see that as those methylene bridges are the closest one to the urea, they are shielded the most, but basically all the signals are very shielded and shifting a lot, which means that in a solution it looks same like in solids. This porphyrin is just sitting from the side of the macrocycle and shielding all the groups and all the protons which are around there. So we did also measurement of CD just to be sure if there is some induction or not. And we were actually quite surprised that there is an induction of CD, because we don't have here some really specific second site which could be interacting to the macrocycle, right? There can be some CH pi interaction from this methylene bridges, and maybe also something weak from this cyclohexano group. But our first thought was that it's maybe more like about repulsion, that we are having binding through the coordination, and then as this molecule is spacious, then the porphyrin has to change its shape a bit to fit close to this molecule. So we studied the binding. We made a NMR and also UV-Vis titrations to have our data from different concentration regions and from independent methods. And you can see that when we used this demethylated monomer of our macrocycle, the binding were pretty low. It was just 50. But in the moment we did the titrations with the macrocycle, you can see that zinc TPP with 6-membered is almost, or it's around 5,000, and with 8-membered, the first association is around 2,000. Moreover, we saw that the binding is not simply 1-to-1, and not even 2-to-1 models were able to fit the data properly. So we had to build our own model to fit 3-to-1 binding, and we were quite successful. So for some of those systems where we did a little bit more excessive amount of titrations in different concentration regions, we were able to fit 3 association constants. However, the second is every time like twice smaller than the first, and so on. So I believe that for 8-membered macrocycle, there's actually maybe even 4 association constants, but the last one is so weak that it's basically impossible to fit it, and there doesn't exist any good model for that. So here is again the structure of the complex, just to see it also different picture than from the crystal. So again, you can see that there is very near those methylene bridges from which the protons can direct to the porphyrin, and actually this fact that with macrocycle the binding is much stronger than with the monomer, it means that there has to be really some additional attractive interaction than just the coordination. Because if this chiral distortion would be caused by repulsion, then we should expect rather decrease in the association constant compared to the binding of monomer. But this is other way around in like really strong way. This is 100 times stronger than binding of a simple monomer unit. Okay, so that was about cyclohexanol hemicucurbituryls, and on this slide I just want to show also the data for biotinuryl, which we are working with, because it was quite surprising when we test the interaction with the biotinuryl. We thought that maybe it will give us some similar strong association as those cyclohexanol hemi-CBs. But here you can see that the binding was much weaker. I can't say how much it was exactly, because it was possible to fit it with 1-to-1 model and also 2-to-1 model, getting kind of similar values. So then it's hard to decide which model is more proper, right? There is definitely enough of groups to have 2-to-1 interaction, but if it's too weak, then just can't rely on those numbers. However, from the overall look of a spectra and how many equivalents of compounds we needed to get the change in the UV-Vis and so on, it was clear that the biotins are binding the porphyrin much weaker than our cyclohexanol hemi-CBs. So what can be behind it? Well, one option would be that maybe there is some additional sites which can compete the interaction. There's another carbonyls from this carboxylic group, or ester in this case. The structure is from the structure is wrong here. This is just the acid, but we were using methyl ester, so here should be methyl. And but most likely the thing is just spherical hindrance, because this molecule, when you look on it, it looks like this scent clock a bit. and those sulfurs are pointing rather like out of the cavity, and also there can be hanging around those long chains and being in the way. But in the case of cyclohexanohemi-Cb, it's much more compact and easier to imagine that there is enough space for this porphyrin without being bothered by some molecule chains, for example. So that's basically what I wanted to show you. So now some summary. I would say we are able to calculate pretty well the CD spectra from our complexes and predict them, which can be a very useful tool for the future, because we definitely want to deal a bit more with this induction of circular dichroism, induction of chirality on the porphyrins. Then, as I just said, the chirality can be induced on suitable achiral molecules, and this is something general. It doesn't work only for the porphyrins. It's a general thing. In general, the supramolecular interactions can be used for that. So we believe we could build some ternary complexes where we are using porphyrin as a probe, which is colorful, and then combining it with some other molecules to give some additional spot for recognition. When we are dealing with studying some complexes, the evaluation of stoichiometry and association constants can be very challenging, and it's important to say those two things goes every time strongly together. You can, of course, every time just fit your data with one-to-one model, but it can look nice, but it doesn't have to be true, and it can be other way around. You think that you have 2-to-1 binding, but in real, it can look nice on the first sight you're fitting, but the reality can be somewhere different. So you need to be sure about your stoichiometry if you want to evaluate the association. Otherwise, you're getting numbers which doesn't make any real sense. We were successful with building our own 3-to-1 model. It's necessary to say that we had to use some specific restrictions which were reasonable to do for this particular system, but it would not work for some other systems. So you need to know what you're doing, and you need to get rid of some variables. Otherwise, again, it's almost impossible to fit those higher binding models than 2-to-1, which are available on the internet. And we were combining, to get these values of association constants, we had to really combine different methods. So mainly we were using UV-Vis, NMR, but we also checked with ITC, which was very useful. And finally, our research showed that our cyclohexanohemicucurbituryls are really well pre-organized for interaction with the planar porphyrins. We are not sure why. Probably there is this CH-pi interactions. However, you saw from the association constants that it really fits with each other very nicely. So last but not least I would like to thank to Professor Rina Af for supervising this work and for making all those nice collaboration and good mood in our group. I think we have really productive group, and we have good relationships, so the work goes nicely. And of course, I want to thank for the sources of money and this Initio project, an opportunity to present this work, and thank you for your attention.
Okay, thank you, Lukash, for the presentation. We are a little bit later for the time. I don't see questions, so I would like to thank you again.